Hi everyone. Today we are discussing about the metallic bonding. In the previous videos we discussed different types of bonding such as covalent bond, ionic bond, etc. And in the very recent videos we have seen the partial ionic character of covalent bonding and partial covalent character of ionic bonding, that is Fajans rule. Today we are discussing a totally different types of bonding, that is metallic bonding, or the bond which is present in different metals, that is called metallic bonding. Now this metallic bonding is entirely different from the ionic bond or a covalent bond, or we can say this is having the characteristics of both ionic as well as covalent bonding. So in order to explain the bonding in metals, several theories are proposed. Because we know the metals are having vast difference in properties. They have a large number of properties because in the periodic table when you consider many of the or majority of the elements are metals. So they show different or we can say unique properties, and these properties vary from metals to metal. So the different properties exhibited by metals include, first of all, their conductivity. We know metals are having good electrical and thermal conductivity. They can easily conduct heat and electricity, and that is because they have a large number of valence electrons. Their valence electrons are delocalized over the metal lattice. And another property of metals is their high tensile strength. We know metals are having high tensile strength. Then they are having malleability, a property called malleability, and also ductility. Malleability means they can be hammered into different shapes, and ductility means they can be drawn into wires. So these are all unique properties of metals, and in addition the metals possess a property called metallic luster. They appear shining. If we cut the metal surface or metal, it shows a shining appearance. When light falls on metals, it shines. So that is called metallic luster. So these are the different properties of metals, and we can explain all these properties of metals based on different theories proposed to explain metallic bonding. So in this video we can discuss in detail the different types of different theories put forward to explain the bonding in metals or metallic bonding. First of all, let's discuss the first theory proposed to explain metallic bonding, that is called the classical free electron theory. The free electron theory, which is proposed by Drude and Lorentz. And this theory, it is the first attempt to explain metallic bonding. And according to free electron theory, as per the name indicates, a metal lattice means we have a number of positive ions which are immersed in a sea of electrons. So a metal or a metallic bond is formed by formed by the attraction between a number of metal ions with the sea of electrons, or we can say the metal ions are immersed in a sea of electrons. Sea of electron in the sense the valence electrons of the metal. We know metals are having very low ionization energy. That means their valence electrons are loosely bound, and these valence electrons, when we consider a metallic lattice, we have a large number of metal atoms. It is not just one or two atoms, but we have a large number of metal atoms. So all these metal atoms are having valence electrons, and these electrons are distributed over the entire metal lattice. So we can consider a metallic bonding or a metal lattice as an assembly of positive charged metal ions immersed in a sea of electrons. So we have positive and negative charges. So obviously the electrostatic force of attraction which binds the positive ions with the sea of electrons, that is called a metallic bonding according to Drude and Lorentz classical free electron theory. So once again, a metallic bond is formed by the electrostatic attraction existing between positive charged metal ions with the sea of electrons. So this is here it is electrostatic. As per free electron theory, metallic bond is formed by electrostatic interaction. So This theory could explain many of the properties of metals, and we know the main essence of this theory is the presence of free electrons over the metal lattice. So because of the presence of this free electrons, delocalized electrons, many of the theories could be, many of the properties of the metals could be explained. First of all, let's see the most important property of metals, that is conductivity. We know conductivity means electrical conductivity as well as thermal conductivity. First, let's see the electrical conductivity. We know when an electric field is applied, because of the presence of free electrons, that charge can be carried from one part to another part easily with the help of free electrons. So in this way, the theory could explain the electrical conductivity of metals. The presence of free electron make it possible for the conduction of charge from one part to another part in the presence of an electric field. And in the same way, the theory can explain the thermal conductivity. That is, when one part of a metal is heated, we know the electrons, the free electrons present at that part, they acquire kinetic energy, and this energy will be transferred, or the thermal energy, heat energy will be transferred over the entire metal lattice with the help of this free electron. So in this way, due to the presence of free electron or with the mobility of free electrons, electricity and heat can be conducted over the metal lattice. That is the explanation of conductivity of metals by free electron theory. Second property, another important property of metals is metallic luster. Metallic luster means, we know when you cut a metal, it shows a shining appearance, and if when light falls on metals, there will be a shining appearance. So that is called metallic luster, and this metallic luster occurs because when we have a metal surface, and when light is falling on a metal surface, there are many free electrons. We know there are free electrons available over the metal lattice. So this radiation induces the electrons to move or to oscillate to and fro. The electrons will be oscillated to and fro by the applied radiation. When electromagnetic radiation is falling on the metal surface, the free electrons tend to oscillate to and fro. Now we know any oscillating electric charge can emit radiation. Okay, so that is a general principle. Whenever you have a moving charge, an oscillating charge, it is capable of emitting radiation. So when light falls on a metal surface, it seems as if the light is being reflected back. So here actually it is not reflecting back. What is happening is, when the light falls on the surface, this light induces the free electrons to oscillate to and fro, and the oscillating electric charge now emit radiation. So it seems as if the incident light is being reflected back, and because of this reflection, the metal surface shows shining appearance. So that is called metallic luster. Next property of the metal is malleability and ductility. We know malleability means the metal can be drawn into, it can be hammered into different shapes, and ductility means the metals can be drawn into wires of different shapes anyway, and that means the metal surface we can make it into different shapes easily. That property is called malleability and ductility. So this malleability and ductility is mainly due to the presence of non-directional bonds in metals. We have seen that in metallic bonding or in metal lattice, we have different metal ions. Positive metal ions are immersed in a sea of electron. So we have alternatively positive, negative and ions. So many ions immersed in a sea of electron. So it is clear that the bonds are not specific directional. They are non-directional in nature. That means bond can be formed and broken easily from one side to another side. Okay, so you have there is electrostatic bond, means it is electrostatic attraction. So this electrostatic attraction existing between the metal ions and electrons, this is non-directional in nature. That means it is uniform in all direction. So because of this non-directional property of metallic bonding, we can have bond breakage and new bond formations are easier. Okay, even if one part of the metal, part is of, or even if one bond is broken, new bonds can be easily formed at other parts. So this make possible these properties, malleability and ductility. They can be hammered or they can be drawn into wires. So these are all due to the non-directional behavior of the metallic bonding. Next property of the metals is their tensile strength. They have very good tensile strength. Tensile strength means they resist stretching without breaking. So this high tensile strength is obviously due to the presence of strong electrostatic attraction between metal ion and the electron. So whenever we have electrostatic attraction, an electrostatic interaction between the particles or in a core, that will give high tensile strength to the compound. So because of that, the metals are also having high tensile strength. Another property of metal is elasticity. Elasticity means when we apply a deforming force, after the removal of deforming force, the substance regain its original shape. So that is the property of elasticity, and this elasticity is also due to the presence of delocalized bonds. We know the metals are having delocalized bond over the entire metal lattice. So even if we have already seen, even if one part of the metal is broken, new bonds are formed easily on other side. So this will give a good elasticity to the metal, and in this way the theory could explain elasticity of metals. So these are the different properties of metals which could be explained by the free electron theory. That is, first of all we have conductivity, thermal conductivity, electrical conductivity, metallic luster, then malleability, ductility, tensile strength and elasticity. All these properties could be explained with the help of free electron theory. Still, the theory had some limitations. The limitations are, even though the theory could explain most of the properties of metals, it could not explain the vast difference in property. That means certain metals are having one particular property, like one extremity, while certain other metals are in the other extreme. So this variation in properties. For example, some metals are very good conductors, but some are insulators. And certain metals like lithium, sodium, etc., they are very soft and they're very soft in nature, but certain other metals are very hard, like osmium. It is very hard in nature, and certain metals have very low melting point, while some other metals have very high melting point. So this variation in properties could not be explained by classical free electron theory. So that was the limitation of this theory. And these limitations were overcome in the next theory. That is, the next theory proposed to explain metallic bonding was valence bond theory, VB theory. So let's see valence bond theory of metallic bonding. This theory was proposed by Pauling, Linus Pauling, and according to valence bond theory, metallic bond is formed by the formation of resonating covalent bonds. That means here comes the concept of covalent bonding. We have seen in free electron theory, the metallic bonding is formed by pure electrostatic attraction, but here it is as per VB theory, metallic bonding is formed by covalent interaction, or we can say it is not pure covalent bond, but it is a resonating covalent bond. So let's see what is the concept of resonating covalent bonds. Let's take potassium metal. So in the case of a potassium metal lattice, we have different atoms, and as per this valence bond theory, these bonds can be resonate, or this can resonate, and this resonance result in additional valencies rather than the normal valency. That means at any time you can have K plus or K minus. So this resonance, the presence of resonance enables additional valencies for the metals. So this is the concept of resonating covalent bonds. So whenever there is resonating covalent bonds, it is not like the normal covalent bond, and because of this resonating nature, it is also here also we can explain most of the properties of metals due to the resonating covalent nature, because the bonds are forming and breaking at different parts. In the same metal lattice, there is simultaneous formation and breakage of bonds at different parts of the metal lattice. So this resonance permits the conductivity, good conductivity of heat and electricity, and also other properties of metals. All the properties like malleability, ductility, tensile strength, etc. can be explained by the resonating covalent bond concept. And also we know whenever there are resonance structures, when we have more canonical structures due to resonance, that will give extra stabilization energy, that is called cohesion energy. Cohesion energy means the resonance, the process of resonance gives extra stabilization energy, and this gives high conductivity and high tensile strength, etc. So that is the concept of valence bond theory, that is metallic bonding is formed by resonating covalent bonds. And also we know in the case of potassium, if you consider potassium atom, because of this resonance it can have additional valencies. Okay, so because of that it makes available the electrons, the orbitals which are capable of accepting electrons, and thereby conduction can be made possible. In order for conduction to occur, there must be electrons. Electrons must be excited from an occupied orbital to a vacant orbital. So this process of resonance allows the existence of vacant orbitals and also filled orbitals, and thereby conductivity can be made possible. So this is the VB theory of metallic bonding. This theory also could explain most of the properties, but the later more authentic theory, that is the band theory, was proposed to explain all the features of a metallic bonding. So let's see the next theory, that is molecular orbital theory, or otherwise called band theory, to explain metallic bonding. So here MO theory is just like in the same way we explain covalent bonding, molecular orbital theory of covalent bonding. Here we can explain the same molecular orbital theory for metallic bonding. Okay. We know, according to molecular orbital theory, the atomic orbitals of the combining atoms, they will overlap, or they will combine to form molecular orbitals. So the number of molecular orbitals formed will be equal to the number of atomic orbitals combining. So when we take an example, lithium metal, we know the configuration of lithium is 1s2, 2s1. So that means the valence shell 2s is containing 1 electron. So when you have two lithium atoms, the 2s atomic orbitals of lithium combine to give two molecular orbitals. One is the bonding molecular orbital and other is the anti-bonding molecular orbitals. So we will have total 2 electrons. When we have 2 lithium atom, total 2 valence electrons. So the 2 electrons occupy the bonding molecular orbital. Suppose we have 3 lithium atoms. So the 3 lithium atoms combine to give 3 molecular orbital, a bonding molecular orbital, a non-bonding molecular orbital, and an anti-bonding molecular orbital. So in this way, whatever be the number of atomic orbitals combining, that much number of molecular orbitals are formed. So in the case of 4 lithium atom, the total number of electrons is 4 because each lithium atom has 1 valence electron. So we can see whatever be the number of lithium atoms, there will be an equivalent number of molecular orbitals formed. And in the case of metals, since there are enormous number of metals, their energy levels comes very close together. Their energy levels are very close, so that now the molecular orbitals exist in the form of a band. Rather than different molecular orbitals, they exist like a band. Due to the formation of these bands, the theory is called band theory. Molecular orbital theory is otherwise called band theory. Because band, in the sense, we know when we have large number of atoms, metal atoms, they combine to form different molecular orbitals. So when the number of atoms increases, the energy separation between the molecular orbitals decreases. So the energies now become a continuous energy rather than discrete energy levels. With increasing number of atoms, we can have a continuous energy levels, or it can be called as a band. Now we cannot differentiate it into different molecular orbital, rather it is observing as a band of energy. So we can call it as a 2s band. And in the case of lithium atom, we know each lithium atom has one electron only. So always only half of the molecular orbitals are filled in the case of lithium metal. So when we have two lithium atoms, only the bonding orbital will be filled and the bonding will be vacant. So in that way, whatever be the number of lithium atoms in the metal lattice, only half of the 2s band will be filled and the other half will be empty. Okay, so here the lower half only will be filled and the other half is vacant. So this existence of vacant and filled levels of the same energy makes the conduction easier process. Okay, so this way we can explain the conductivity of metals. It can easily conduct electricity because these are all of the same energy level, and there are electrons in the within the 2s band we have filled levels and vacant levels. So electrons can be easily transferred to the vacant levels and thereby conduction can be made possible. So this is for lithium atom. But when we consider another case, say beryllium, you have beryllium metal and the configuration of beryllium is 1s2, 2s2. So the 2s, when we consider the valence shell alone, the 2s band is, we know, when you have two beryllium atom, there are 4 electrons. So the 2 will be occupied in the bonding molecular orbital and 2 will be in the anti-bonding when you have 2 beryllium atom. So depending on that, in the metal lattice we know there are a vast number of metal atoms. So here also a band is formed that is called 2s band. But when compared with beryllium, when compared with lithium in the previous case, here the difference is the 2s band is totally filled because the valence configuration of beryllium is 2s2. That means each atomic orbital is having 2 electrons. So whatever be the number of molecular orbitals formed, all of them will be filled. So here, if that is the case, we have to think how the conduction is possible. So here we have to see the 2p also. We know there is a 2p subshell, and the 2p subshell is vacant in the case of beryllium atom or beryllium metal. So in addition to this 2s band, we have a vacant 2p band also. There is a vacant 2p band, and this 2s band is completely filled, but 2p band is fully vacant. So at some points there will be some exchange of energy. So energies can be varied at different points and at equilibrium points there comes a very less band gap between the 2s and 2p, or we can say they can sometimes be overlap at some cases. Okay, so this at this point, that is when the energy difference between 2s and 2p is very low, electrons from 2s band can be excited to the 2p band and thereby conduction can be made possible. So this way the theory could explain the conductivity in metals. That is, as per molecular orbital theory or band theory, the atomic orbitals of metals combine to give molecular orbitals. Since in a metal lattice we have enormous number of metals, we can have a large number of molecular orbitals, and because of the presence of infinite number of molecular orbitals, their energy exists as a continuous energy, or we can call it as a band. Rather than different discrete molecular orbitals, it exists as a band. So we can call as 2s band, 2p band, etc. And in the case of lithium, we know the 2s band is half filled, so the conduction is very easy. But in the case of beryllium atom, in the second group elements, we have 2s band completely filled, but we have another next higher energy 2p band which is vacant. So at some points, the energies of, when this energies of 2s and 2p comes closer, then the electrons from 2s can excite to 2p band, and this way conduction can be made possible. So now we can conclude this metallic bonding session. Like we have seen the metallic bonding, definition of metallic bonding by different theories. The theories such as classical free electron theory, valence bond theory and molecular orbital theory or band theory. So these theories could explain most of the properties of metals, and also we know the metals, the different properties of metals are due to the special type of bonding, the metallic bonding existing in between them. So according to free electron theory, it is purely electrostatic interaction, that is the free electrons or metal ions are immersed in a sea of electron, and the electrostatic interaction is responsible for the metallic bonding, whereas in VB theory it is the covalent bonding, resonating covalent bonding, and in MO theory also it is the molecular orbital or a band is formed, and the metal electrons are now dispersed in the different bands, different energy band or energy continuous energy levels. So this way these theories could explain most of the properties of metals such as conductivity, thermal conductivity, electrical conductivity, metallic luster, malleability, ductility, tensile strength and elasticity. So that is all about metallic bonding. Thank you.